Tonight, we're going to explore one of the most violent and extreme phenomena in the entire universe. Imagine an object the size of a city, just 12 miles across, yet containing more mass than our entire sun, spinning so fast that its surface moves at a quarter of the speed of light. Not once every few hours. Not once a minute. Some of these objects complete over 700 full rotations every single second. That's faster than the blades of a kitchen blender. An object with more mass than the sun, spinning faster than a blender. That sounds impossible. It sounds like it should tear itself apart. And yet, these objects exist. They're called neutron stars. And the reason they spin so fast is one of the most elegant and terrifying consequences of physics you will ever encounter. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a massive difference for me. Now, let's begin. Let's start with something you already understand. Gravity. You feel it right now, holding you to whatever surface you're sitting or standing on. It's pulling you toward the center of the Earth. You've lived with gravity your entire life, so it feels normal, gentle even. You drop something, and it falls. You jump, you come back down. Gravity on Earth accelerates objects at about 9.8 meters per second squared. That's comfortable. That's manageable. That's the gravity your bones, muscles, and organs evolved to handle over millions of years. But gravity is not always gentle. Gravity depends on two things: the mass of the object pulling you, and how close you are to its center. The more massive the object, the stronger its pull. The closer you are to its center, the stronger the pull becomes. On Earth, you're standing about 6,371 kilometers from the planet's center. The Earth has a mass of about 6 trillion kilograms. These two numbers, the mass and the distance, determine the gravity you feel. Change either one, and the gravity changes. On the Moon, gravity is about 1/6 of Earth's. The Moon is less massive, so it pulls less strongly. On Jupiter, gravity is about 2.5 times stronger than Earth's. Jupiter is far more massive. On the surface of the Sun, if you could somehow stand on it, gravity would be about 28 times stronger than on Earth. The Sun contains about 330,000 times more mass than Earth, but it's also much larger, so the surface is farther from the center. These two effects partially cancel each other out, giving you 28 times Earth's gravity rather than 330,000 times. Now here's where things get extreme. Imagine you could take the entire mass of the Sun, all 330,000 Earth masses worth of material, and compress it. Squeeze it down. Make it smaller and smaller. As you compress it, the surface gets closer to the center. And as the surface gets closer to the center, gravity at the surface increases. Not a little. A lot. Because of how rapidly gravity strengthens as distance shrinks. It follows what's called an inverse square law. If you halve the distance to the center, gravity doesn't just double, it quadruples. If you reduce the distance by a factor of 10, gravity increases by a factor of 100. If you reduce the distance by a factor of 1,000, gravity increases by a factor of 1 million. This is exactly what nature does when it creates a neutron star. A neutron star is what's left behind when a massive star dies in a catastrophic explosion called a supernova. When that explosion happens, the core of the dying star collapses under its own gravity. It collapses so violently and so completely that the atoms themselves are crushed. Electrons are forced into protons, creating neutrons. The entire core, containing more mass than our Sun, is compressed into a sphere about 20 kilometers across. About 12 miles. That's roughly the size of a city. Manhattan Island is about 21 kilometers long. A neutron star would fit comfortably within the boundaries of a single city. Think about what that means. Take every bit of mass in the Sun, every atom, every particle. The Sun is so large that 1.3 million Earths could fit inside it. Now take all of that mass and crush it down until it fits within a space the size of a city. The density is beyond anything you can intuitively grasp. A single teaspoon of neutron star material would weigh about 4 billion tons. Not a million. Billion. 4 billion tons in a teaspoon. That's roughly the weight of a mountain compressed into a volume smaller than a sugar cube. If you could somehow transport a teaspoon of neutron star material to Earth, it would be so heavy that nothing could support it. It would fall straight through the ground, through the Earth's crust, through the mantle, and settle at the center of the planet. Not because it's particularly large, it's still just a teaspoon, but because the gravitational pull of that much mass concentrated in that small A volume is extraordinary. The gravity on the surface of a neutron star is about 200 billion times stronger than gravity on Earth. If you weighed 150 pounds on Earth, you would weigh about 30 trillion pounds on a neutron star. Of course, you wouldn't actually stand on a neutron star. You'd be instantly crushed into a thin layer of atoms on the surface. The gravitational force would flatten you so completely and so quickly that you wouldn't even have time to register what was happening. Every cell in your body, every molecule, would be pulled down with a force billions of times stronger than anything your body was designed to handle. Your entire body would be compressed into a film thinner than a sheet of paper in a fraction of a millisecond. Not because of heat or radiation, but simply because of gravity. Pure, overwhelming, inescapable gravity. The tallest mountain that could possibly exist on a neutron star's surface would be less than a millimeter high. Gravity pulls everything flat. There are no hills, no valleys, no terrain features of any kind that your eye could detect. The surface is smoother than the smoothest ball bearing ever manufactured on Earth. Ground perfectly flat by gravitational force that tolerates no imperfection. If you dropped an object from a height of 1 meter above the surface of a neutron star, it would hit the surface traveling at about 7 million kilometers per hour. That's more than 0.5% of the speed of light, from a drop of 1 meter. On Earth, an object dropped from the same height hits the ground at about 16 kilometers per hour. On a neutron star, the same drop produces a speed 400,000 times faster. The impact would release energy comparable to a nuclear weapon. Not because the object is special, but because gravity is pulling it down with such unimaginable force. Light itself is affected by neutron star gravity. Photons leaving the surface of a neutron star lose energy climbing out of the gravitational well. This is called gravitational redshift. On a neutron star, the redshift is significant. Light leaving the surface arrives at a distant observer with noticeably less energy than when it started. Space and time are warped around these objects in ways that become directly observable. If you looked at a neutron star from a safe distance, you'd actually be able to see part of its far side. The gravity is so strong that it bends light around the star, allowing you to see more than half its surface at once. The star literally curves the space around it so much that light wraps partway around it. The interior of a neutron star is one of the most extreme environments in the known universe. The outer crust is made of a lattice of iron nuclei, incredibly rigid, about 10 billion times stronger than steel. Below that is the inner crust where neutrons begin to drip out of the nuclei, forming a superfluid. Deeper still, the core is made almost entirely of neutrons packed together at densities exceeding that of an atomic nucleus. And at the very center, physicists aren't entirely sure what exists. The pressures and densities are so extreme that matter might take on forms we've never seen. Some theories suggest quarks might become deconfined, forming a quark-gluon plasma. Others suggest exotic particles called hyperons might appear. We simply don't know because we can't recreate these conditions on Earth. Even our most powerful particle accelerators can't sustain the pressures found in a neutron star's core. The magnetic fields of neutron stars are also extraordinary. A typical refrigerator magnet has a magnetic field of about 5,000ths of a Tesla. An MRI machine in a hospital operates at about 1.5 to 3 Tesla. The Earth's magnetic field is about 50 millionths of a Tesla. A typical neutron star has a magnetic field of about 100 million Tesla. That's roughly 2 trillion times stronger than the Earth's magnetic field. And some neutron stars called magnetars have magnetic fields 1,000 times stronger still, reaching 100 billion Tesla. A magnetar's magnetic field is so powerful that it would be lethal from a distance of about 1,000 kilometers. At that range, the field would distort the electron clouds around atoms in your body, disrupting the chemistry that keeps you alive. The field would essentially rip apart the molecular bonds that hold your cells together. These magnetic fields aren't just impressive numbers, they have real physical consequences. The magnetic field of a neutron star channels charged particles along its field lines, creating beams of radiation that shoot out from the magnetic poles. As the neutron star rotates, these beams sweep through space like a lighthouse beam, sweeping across the ocean. If one of those beams happens to sweep across Earth as the star rotates, we detect a pulse of radio waves, or sometimes X-rays or gamma rays. This is what makes a pulsar. We'll talk much more about pulsars later, but for now, the important point is this. Those pulses come at incredibly regular intervals. And by measuring the interval between pulses, we can determine exactly how fast the neutron star is spinning. And this is where things get truly mind-bending. Some neutron stars spin slowly, completing one rotation every few seconds. That might not sound slow, but for a neutron star it is. Others spin faster, completing a rotation every fraction of a second. The Crab pulsar, which sits at the center of the Crab Nebula and is the remnant of a supernova observed by Chinese astronomers in the year 1054, rotates about 30 times per second. 30 full rotations every single second. This object is about 20 kilometers across, contains more mass than the Sun, and it's completing 30 full rotations in the time it takes you to blink. But even the Crab pulsar is slow compared to the fastest neutron stars. The fastest known neutron star, a millisecond pulsar designated PSRJ 1748-2446 AD, rotates at 716 times per second. 716 full rotations every second. The equator of this neutron star is moving at about 24% of the speed of light. Nearly a quarter of the speed of light. For an object containing more mass than the Sun. Let me try to put that rotation rate in perspective. 716 rotations per second means that one full rotation takes about 1.4 milliseconds. In the time it takes you to snap your fingers, roughly 300 milliseconds, this neutron star has completed over 200 full rotations. In one heartbeat, about 1 second, it rotates 716 times. In the time it takes you to say the word spin, it has already spun hundreds of times. If you could somehow see this object rotating, it would be a blur. Actually, it wouldn't even be a blur. It would be beyond anything your eyes or brain could process. Your visual system can process roughly 60 to 90 images per second. This star is rotating nearly 8 times faster than your brain can form images. It would appear as a perfectly smooth, unchanging sphere because your eyes literally cannot keep up. Now pause and think about what this means physically. The surface of this neutron star at its equator is moving at over 70,000 kilometers per second. At that speed, you could travel from New York to Los Angeles in about a 16th of a second. You could circle the entire Earth in roughly half a second. You could travel from Earth to the Moon in about 5 seconds. The surface is moving so fast that the centrifugal effect, the outward push created by the rotation, is actually significant even against the crushing gravity of the neutron star. In fact, if the star were spinning just a little bit faster, the centrifugal force at the equator would overcome gravity, and the star would tear itself apart. These fastest spinning neutron stars are operating near their structural limit. They're spinning almost as fast as physics allows before the object would be ripped to pieces by its own rotation. This is the puzzle we need to solve tonight. How does this happen? How does an object so massive, so dense, with gravity so strong that it visibly warps the light leaving its surface, end up spinning this fast? It seems contradictory. Massive objects should be slow and ponderous. Heavy things are hard to spin. If you've ever tried to spin a heavy wheel, you know it takes a lot of effort to get it going. Heaviness and rapid spinning seem like opposites. And yet, neutron stars combine both. They are among the most massive and dense objects in the universe, and they are among the fastest spinning. This combination seems impossible, but it's not. And the reason it's not impossible comes down to one of the most fundamental and beautiful laws in all of physics. To understand that law, let's step away from neutron stars for a moment and talk about something much more familiar. Spinning. You've watched things spin your entire life. Tops, wheels, merry-go-rounds, ceiling fans. Spinning is one of the most common types of motion in the universe. Planets spin, stars spin, galaxies spin, even atoms, in a quantum mechanical sense, have a property called spin. Rotation is everywhere, but spinning isn't random. It follows rules, and one of the most important rules governing rotation is something you've probably experienced without ever knowing its name. Imagine a child sitting on a merry-go-round at a playground. Someone pushes the merry-go-round, and it starts spinning. Now, the child is sitting near the edge, holding on. As the merry-go-round spins, the child feels a force pushing them outward. That's the centrifugal effect. The faster it spins, the stronger that outward push. This is familiar. Everyone has felt it. Now imagine the child lets go of the edge and crawls toward the center of the merry-go-round. What happens? If you've ever tried this, you know the answer. The merry-go-round speeds up. It starts spinning faster as the child moves toward the center. Nobody pushed it harder. Nobody added energy to the system. The child simply moved closer to the center, and the rotation rate increased on its own. This seems almost magical. Where did the extra speed come from? The answer is that it was always there. It was always contained in the system. When the child was at the edge, the rotation was slower because the mass was spread far from the center. When the child moved to the center, bringing the mass closer to the axis of rotation, the rotation had to speed up to compensate. The total amount of rotational motion stayed exactly the same. It just expressed itself differently. This is conservation of angular momentum. It's one of the most fundamental laws in physics, as fundamental as conservation of energy or conservation of regular momentum. It cannot be violated. It applies to everything, from playground equipment to galaxies, from figure skaters to dying stars. You've seen this principle in action many times without knowing it. Think of a figure skater performing a spin. The skater begins with their arms extended, spinning slowly. Then they pull their arms in close to their body. Instantly, dramatically, their spin rate increases. They go from a slow, graceful rotation to a rapid blur in less than a second. They haven't pushed off the ice again. They haven't gained any energy from an outside source. They simply pulled their mass closer to their axis of rotation, and the spin rate increased to conserve angular momentum. This is the key principle. When a spinning object gets smaller, when its mass moves closer to the axis of rotation, it must spin faster. Not because something is pushing it faster, not because energy is being added, but because angular momentum must be conserved. It's a law of nature as ironclad as gravity itself. It cannot be cheated, cannot be circumvented, cannot be switched off. It applies always and everywhere, from the smallest subatomic particle to the largest rotating structure in the cosmos. Let me be a bit more precise about what angular momentum actually is. In simple terms, the angular momentum of a spinning object depends on three things: its mass, how fast it's spinning, and how far that mass is from the axis of rotation. Specifically, it depends on what physicists call the moment of inertia, which is a measure of how the mass is distributed relative to the axis. An object with its mass concentrated far from the axis has a high moment of inertia. An object with its mass concentrated near the axis has a low moment of inertia. Conservation of angular momentum says that if no outside force acts on a spinning system, its angular momentum stays constant. If the moment of inertia decreases, meaning mass moves closer to the axis, the spin rate must increase to keep the total angular momentum the same. If the moment of inertia increases, meaning mass moves farther from the axis, the spin rate must decrease. It's a perfect trade-off. Mass distribution and spin rate are linked in an unbreakable relationship. The figure skater is a perfect example. Arms out, the mass is far from the axis, and the moment of inertia is high. The skater spins slowly. Arms in, the mass is closer to the axis, and the moment of inertia is low. The skater spins fast. The angular momentum stays the same in both cases. The skater didn't create or destroy rotational motion. They just redistributed it. But here's the crucial detail that makes this relevant to neutron stars. The relationship between the spin rate and the size of the spinning object is not linear. It follows a square law. If you reduce the radius by a factor of 2, the spin rate increases by a factor of 4. If you reduce the radius by a factor of 10, the spin rate increases by a factor of 100. If you reduce the radius by a factor of 1000, the spin rate increases by a factor of 1,000,000. Think about what that means. A small change in size produces a large change in spin rate, and a large change in size produces an enormous change in spin rate. This is why the figure skater analogy, while useful, barely scratches the surface of what happens with the neutron stars. The skater pulls their arms in, reducing their effective radius by maybe a factor of 2. Their spin rate roughly quadruples. That's impressive and beautiful to watch, but it's nothing compared to what happens during the collapse of a stellar core. When a massive star dies and its core collapses to form a neutron star, the change in size is not a factor of 2. It's not a factor of 10. It's not even a factor of 1,000. The core of a massive star before collapse is roughly the size of the Earth, about 12,700 kilometers in diameter. After a collapse, the neutron star is about 20 kilometers in diameter. That's a reduction in radius by a factor of more than 600. And because angular momentum conservation follows a square law, the spin rate increases by a factor of hundreds of thousands of times faster. A stellar core that was lazily rotating once a month, so slowly you'd never notice it without instruments, becomes a neutron star spinning dozens or even hundreds of times every single second. A rotation rate so slow it was essentially invisible transforms into one so fast that the surface moves at a significant percentage of the speed of light. And the original angular momentum hasn't changed at all. Not one bit of rotational motion was added. The collapse simply concentrated what was already there into a much smaller space. We'll walk through the exact numbers later when we trace the death of a massive star step by step. But the principle is clear. A slow spin becomes a fast spin, purely because the object shrank, all because angular momentum must be conserved, all because of that square law relationship between radius and rotation rate. This is why neutron stars spin so fast. It's not because some mysterious force spins them up. It's not because the supernova explosion somehow adds rotational energy. It's because the object that became the neutron star was already spinning, even if slowly. And when it collapsed, when its radius decreased by a factor of hundreds, its rotation rate had to increase by a factor of hundreds of thousands. The angular momentum was already there. It was always there. It just became visible, became dramatic, became extreme when all that mass was crushed into a space the size of a city. This is one of those moments in physics where a simple law, conservation of angular momentum, produces a result so dramatic that it seems almost impossible. The elegance is breathtaking. The same law that makes a figure skater spin faster when they pull in their arms is the same law that makes a 20-kilometer sphere of neutrons spin hundreds of times per second. The physics is identical, only the scale is different. And the scale is very, very different. The skater changes their radius by a factor of maybe 2. The collapsing star changes its radius by a factor of more than 600. The skater's spin rate increases by a factor of maybe 4. The star's spin rate increases by a factor of hundreds of thousands. Same law, same principle, vastly different consequences. Now, you might be wondering, If nearly all stars spin, and if collapsing makes things spin faster, then shouldn't every neutron star be spinning incredibly fast? The answer is mostly yes. Every neutron star is born spinning rapidly. But not all neutron stars spin at the same rate, because not all stars rotate at the same speed before they die. Some stars rotate faster than others. Some have stronger magnetic fields that slow their rotation before they collapse. The details matter, and they produce a range of rotation rates among newborn neutron stars. But the fundamental story is always the same. A star spins, the star dies, its core collapses. The collapse compresses the core to a tiny fraction of its original size. Angular momentum is conserved. The neutron star spins fast. Incredibly, almost unbelievably fast. And it does this not because of some exotic unknown force, but because of a law of physics so basic that you can demonstrate it on a playground merry-go-round. That's what makes this phenomenon so beautiful. The most extreme spinning objects in the known universe, objects that rotate hundreds of times per second, objects whose surfaces move at significant fractions of the speed of light, are explained by a principle so simple that a child can feel it when they crawl toward the center of a spinning platform. The universe takes simple rules and applies them at scales that produce extraordinary results. A law that barely changes the rotation of a figure skater produces something almost miraculous when applied to a collapsing star. But we've only scratched the surface. We know why neutron stars spin fast. It's conservation of angular momentum during collapse. But there are deeper questions. How exactly does the collapse happen? What determines the final spin rate? And most intriguingly, how do some neutron stars end up spinning even faster than the collapse alone should produce? Because some of those millisecond pulsars, the ones spinning at 700 times per second, are spinning too fast. Even the conservation of angular momentum during collapse can't fully account for their rotation rates. Something else is going on. Something is spinning them up even further after they're born, and that process is, if anything, even more remarkable than the collapse itself. So we know the principle. Conservation of angular momentum means that when a spinning object shrinks, it spins faster. But knowing the principle is not the same as understanding the event. Because the collapse that creates a neutron star is not some gentle, gradual process. It's one of the most violent events in the entire universe. A catastrophe so extreme that it briefly outshines entire galaxies. To truly understand why neutron stars spin so fast, you need to understand what happens to a massive star when it dies. You need to understand the life, the crisis, and the final seconds of a giant. Let's go back to the beginning. Not the beginning of the universe, but the beginning of a star. Stars are born inside vast clouds of gas and dust, called nebulae. These clouds are mostly hydrogen, the simplest and most abundant element in the universe, with some helium mixed in and trace amounts of heavier elements. A typical stellar nursery might stretch across dozens of light years and contain enough gas to form thousands of stars. Inside these clouds, gravity is always at work. Any region that happens to be slightly denser than its surroundings pulls in a little more gas. As more gas accumulates, the gravitational pull grows stronger, attracting even more gas. This is a runaway process. Once it starts, it accelerates. The gas falls inward, compressing and heating up. Over hundreds of thousands of years, the collapsing region forms a dense, hot core called a protostar. This protostar continues to accumulate mass from the surrounding cloud, growing larger and hotter. Here's a detail that matters enormously for our story. The gas cloud from which a star forms is never perfectly still. It always has some rotation, even if it's very slight. Maybe a nearby supernova gave the cloud a gentle push on one side. Maybe gravitational interactions with other clouds introduced a small amount of spin. Whatever the cause, the cloud is rotating, even if incredibly slowly. A typical molecular cloud might take millions of years to complete a single rotation. That's so slow you'd never notice it. But it's not zero. And that matters. As the gas collapses inward to form a star, conservation of angular momentum is already at work. The cloud is large, perhaps several light years across. As it contracts to form a star that's only a few million kilometers across, the radius decreases by a factor of millions. And just like the figure skater pulling in their arms, the rotation rate increases. By the time the gas has contracted from a cloud spanning light years to a star spanning millions of kilometers, the rotation has increased dramatically. This is why all stars rotate. Not because something spins them up after they form, but because the gas clouds from which they condensed were already rotating, even if imperceptibly slowly. The collapse amplifies that tiny initial rotation into something measurable. Our Sun, for example, rotates once about every 25 days at its equator. That rotation is a relic of the angular momentum that existed in the gas cloud from which the Sun formed 4.5 billion years ago. But here's where things diverge. Not all stars are the same size. Some stars form with just a fraction of the Sun's mass. These small red dwarfs burn their fuel slowly and live for trillions of years. They will never produce neutron stars. They don't have enough mass. Other stars form with masses similar to the Sun's. These middleweight stars live for billions of years and eventually end their lives as white dwarfs, dense but comparatively gentle remnants. They don't produce neutron stars either. The stars we care about tonight are the heavyweights. Stars are born with at least 8 times the mass of the Sun, and sometimes 20 or 30 or even 50 times the Sun's mass. These are the stars that will one day collapse to form neutron stars, and their lives, while spectacular, are surprisingly short. A star like the Sun lives for about 10 billion years. It burns its hydrogen fuel slowly and steadily. But a star with 20 times the Sun's mass doesn't live 20 times longer. It lives a much shorter time because massive stars burn their fuel at a ferocious rate. The more massive the star, the higher the temperature and pressure at its core, and the faster it consumes its nuclear fuel. A star 20 times the mass of the Sun lives for only about 10 million years. That might sound like a long time, but compared to the Sun's 10 billion years, it's an eye blink. The most massive stars, those with 50 or more solar masses, might live only a few million years. They burn through their fuel with reckless speed, blazing brilliantly but briefly across the cosmic stage. During their lives, these massive stars are extraordinary objects. They're enormous, often tens of millions of kilometers across. They're incredibly luminous, sometimes hundreds of thousands of times brighter than the Sun. They're hot, with surface temperatures of 20,000 to 50,000 degrees, compared to the Sun's relatively modest 5,500 degrees, and they're constantly losing mass. Powerful stellar winds blow material off their surfaces at speeds of thousands of kilometers per second. Over their lifetimes, these winds can strip away a significant fraction of the star's original mass. A star born with 30 solar masses might have only 15 or 20 solar masses left by the time it dies. These stars also rotate. Some massive stars rotate quite slowly, completing one rotation every few weeks or months. Others rotate much faster. Some young massive stars spin so rapidly that they're visibly flattened at their equators, bulging outward due to centrifugal effects. The rotation rate of the star before it dies will directly influence how fast the resulting neutron star spins. A faster spinning progenitor star produces a faster spinning neutron star, its angular momentum all the way down. Now, let's talk about what's happening inside one of these massive stars. Because the interior of a massive star in the final stages of its life is one of the most remarkable structures in the universe. At the core, nuclear fusion is taking place. Fusion is the process that powers all stars. It works by combining lighter atomic nuclei into heavier ones, releasing energy in the process. The Sun fuses hydrogen into helium in its core. This single reaction has been powering the Sun for 4.5 billion years, and will continue for another 5 billion. It's a steady, reliable process. One reaction, one fuel source, simple and stable. But massive stars are different. They're so hot and so dense at their cores that they can fuse not just hydrogen, but progressively heavier elements. And this is where the story gets dramatic. A massive star begins its life just like the Sun, fusing hydrogen into helium in its core. This hydrogen-burning phase is the longest stage of the star's life, lasting millions of years. But eventually, the hydrogen in the core runs out. When that happens, something crucial changes. Without the energy from fusion pushing outward, the core begins to contract under its own gravity. As it contracts, it heats up, and when the temperature reaches about 100 million degrees, a new reaction ignites. Helium begins fusing into carbon. This helium-burning phase is shorter than the hydrogen phase. The reaction produces less energy per unit of fuel, and the star is burning through its reserves faster. After several 100,000 years, the helium in the core is exhausted. The core contracts again, heats up further, and carbon begins fusing into neon and magnesium. This stage lasts only about 1,000 years. Then neon fuses into oxygen and magnesium over a period of roughly a year. Then oxygen fuses into silicon and sulfur over a period of months. Do you notice the pattern? Each successive fusion stage produces heavier elements, generates less energy, and lasts for a dramatically shorter time. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts about 1,000 years. Neon burning lasts roughly a year. Oxygen burning lasts months. Each stage is shorter than the last by an enormous factor. And then comes the final stage. Silicon burning. Silicon fuses into iron, and this stage lasts roughly 1 day. One single day. After millions of years of hydrogen burning, after hundreds of thousands of years of helium burning, after thousands of years of progressively shorter stages, the star reaches a point where it burns through an entire stage of nuclear fuel in approximately 24 hours. At this moment, the star's internal structure looks like an onion. Layer upon layer, concentric shells of different elements surround the core, each layer representing a different stage of nuclear fusion. If you could somehow slice the star in half and look at its cross-section, you'd see a beautiful and terrifying structure. The outermost shell is still fusing hydrogen. Below that, a shell fusing helium, then carbon, then neon, then oxygen, then silicon, and at the very center the core is now made of iron. Pure iron, compressed to extraordinary density, hotter than almost anything in the universe. And here is where the crisis arrives. Because iron is different from every element that came before it. Every previous fusion reaction released energy. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. Each reaction powers the star, generating the outward pressure needed to support the enormous weight of the material above the core. Fusion is what keeps the star from collapsing under its own gravity. It's the pillar holding up the ceiling. But iron is the end of the line. Iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy. It requires energy. It absorbs energy. It takes energy away from the star rather than providing it. When the core becomes iron, the star has reached a dead end. It's like a fire that has burned through every type of fuel available and now faces a material that cannot burn. The furnace goes cold. For millions of years, the star maintained a delicate balance. Gravity is pulling inward, trying to collapse the star. Fusion is pushing outward, preventing the collapse. This balance, called hydrostatic equilibrium, is what keeps every star stable. But with an iron core, the outward push stops. Gravity, which has been waiting patiently for millions of years, finally wins. What happens next takes less than 1 second. The iron core, which at this point is roughly the size of the Earth, about 12,000 kilometers across, and contains roughly 1.5 times the mass of the Sun, collapses. And when I say collapses, I don't mean it gradually sinks or slowly compresses. I mean, it falls inward at a significant fraction of the speed of light. The core freefalls under its own gravity in about 1/4 second. In the time it takes your heart to complete a single beat, the core goes from Earth-sized to city-sized, from 12,000 kilometers across to roughly 20 kilometers across. It happens so fast that the outer layers of the star don't even know it's happening. Information travels at the speed of light, and even at light speed, the news of the core's collapse takes time to reach the outer envelope of the star. The outer layers are still sitting there, still fusing elements in their shells, completely unaware that the floor has just dropped out beneath them. During this collapse, the matter in the core is compressed to nuclear density. The atoms are crushed. Electrons are forced into protons, converting them into neutrons and releasing a flood of ghostly particles called neutrinos. These neutrinos carry away an enormous amount of energy, roughly 99% of the total energy released by the collapse. The remaining 1% is still enough to blow the entire outer envelope of the star into space at speeds of thousands of kilometers per second. That's the supernova explosion. But the neutrinos carry the lion's share of the energy. In fact, for those brief seconds, the neutrino luminosity of this single dying star exceeds the combined light of every other star in its entire galaxy. One star, in the act of dying, briefly outshines hundreds of billions of living stars. Not in visible light, but in the ghostly energy of neutrinos pouring from its collapsing core. The core collapse happens so rapidly and so violently that it actually overshoots. The core compresses past its equilibrium point, becoming even denser than a neutron star for a brief instant. Then it bounces back, like a rubber ball hitting a concrete floor. This bounce sends a shockwave outward through the infalling material. For decades, astrophysicists thought this bounce alone was enough to power the supernova explosion, blasting the outer layers into space. But detailed computer simulations showed that the shockwave stalls. It runs into the infalling material and loses energy. It doesn't have enough force on its own to expel the outer envelope. This was a major problem in astrophysics for years. We could see supernovae happening. We knew they were powerful enough to blow stars apart, but our models couldn't reproduce the explosion. The shockwave kept stalling. Something else was needed to revive it. The answer, as best we understand it today, is those neutrinos. The flood of neutrinos streaming outward from the collapsed core deposits a small fraction of its energy into the material behind the stalled shockwave. This additional energy revives the shock, pushing it outward again. The shockwave plows through the outer layers of the star, heating them, accelerating them, and ultimately blasting them into space as a supernova remnant. The outer layers are expelled at speeds of up to 30,000 kilometers per second. That's 10% of the speed of light. These layers carry with them all the heavy elements that were forged during the star's life and during the explosion itself. Gold, silver, platinum, uranium, and all the elements heavier than iron are created in the extreme conditions of the supernova explosion or in the moments just before it. These elements are scattered into space, mixing with the interstellar gas, eventually being incorporated into new gas clouds that will form new stars and new planets. Every atom of gold in every wedding ring on Earth was forged in a cataclysmic stellar event billions of years ago, likely the collision of neutron stars or the explosion of a massive sun. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was made inside a massive star and scattered into space when that star died. But while the outer layers are blasted away, the core remains behind. It has collapsed from Earth-sized to city-sized in less than a second. And here is where our central story reaches its climax. Because that core was spinning before it collapsed. The massive star rotated throughout its entire life. The core, sitting at the center of the star, shared in that rotation. It might have been spinning once every 30 days, maybe once every 15 days, maybe once every 60 days. The exact rate depends on the star's history, its mass, its magnetic field, how much mass it lost through stellar winds, and various other factors. Let's walk through the numbers with a specific example. Consider a massive star whose core rotates once every 30 days. That's a rotation period of about 2.6 million seconds. Before collapse, the core has a radius of roughly 6,000 kilometers, similar to Earth's radius. After a collapse, the neutron star has a radius of about 10 kilometers. The radius has decreased by a factor of 600. Conservation of angular momentum tells us that the rotation rate increases by the square of this factor. 600 squared is 360,000. So the rotation period decreases by a factor of 360,000. 2.6 million seconds divided by 360,000 gives about 7.2 milliseconds. That's a rotation period of about 7 milliseconds, which translates to roughly 139 rotations per second. From one single lazy rotation per month to well over 100 rotations per second in less than a heartbeat. The physics is straightforward, but the result is staggering, and this is a conservative example. If the original core was spinning faster, say once every 10 days, the resulting neutron star would spin at over 400 rotations per second. If the core was spinning once every 5 days, you would get close to 1,000 rotations per second. Though at that point, other factors like mass loss during the supernova and interactions between the core and the outer layers would modify the result. The point is that perfectly ordinary rotation rates in a massive star's core, rates so slow they'd be barely noticeable, become extraordinary rotation rates in a neutron star. The collapse amplifies the spin by factors of hundreds of thousands. This isn't exotic physics. This isn't speculation. This is the inevitable, unavoidable consequence of a fundamental conservation law applied to an extreme change in size. Let me give you one more way to visualize this. Imagine you're standing at the equator of the star's core before collapse. The core is roughly the size of Earth, about 40,000 kilometers in circumference. It rotates once every 30 days. At the equator, you'd be moving at about 55 kilometers per hour. That's roughly the speed of a car in city traffic. You wouldn't feel any particular sense of speed. The rotation would be imperceptible without instruments. Now the collapse happens. In less than a second, you've gone from standing on the equator of an Earth-sized object to being on the surface of a 20-kilometer sphere. The circumference has dropped from 40,000 kilometers to about 63 kilometers. But your rotational speed hasn't just stayed the same. Because the angular momentum is conserved and the radius has shrunk enormously, the surface speed has increased dramatically. The equator of the neutron star is now moving at roughly 9,000 kilometers per second. You've gone from city traffic speed to about 3% of the speed of light. From 55 kilometers per hour to roughly 32 million kilometers per hour. In less than 1 second. This isn't just a number. This has physical consequences. At those speeds, the equatorial surface of a fast-spinning neutron star experiences significant centrifugal effects, even against the incredible gravity. The star becomes slightly oblate, bulging at the equator and flattening at the poles. For the fastest-spinning neutron stars, this bulge is measurable. The star is literally being deformed by its own rotation, stretched outward at the equator by the centrifugal effect, while gravity tries to pull everything into a perfect sphere. These two forces compete, and the shape of the star reflects the balance between them. There's another aspect of the collapse that deserves attention. When the core collapses, it doesn't just shrink smoothly and uniformly. The collapse is chaotic and violent. The infalling material doesn't all arrive at the center at the same time or from the same direction. Instabilities develop. The collapsing matter swirls and tumbles. Convection currents form in the proto-neutron star as neutrinos heat the material unevenly. All of this turbulence can affect the final spin rate and the orientation of the spin axis. Computer simulations of core collapse supernovae show that the neutron star can receive a significant kick during the explosion. Asymmetries in how the material is expelled, slight imbalances in the neutrino emission, and instabilities in the shock wave, all of these can give the neutron star a push. Observationally, we know this happens because many neutron stars are moving through space at very high speeds, sometimes hundreds of kilometers per second. They were literally kicked out of their birthplace by an asymmetric explosion. Some of these kicks are so powerful that the neutron star is ejected from its host galaxy entirely, doomed to travel through intergalactic space forever. These kicks can also affect the spin. An asymmetric explosion doesn't just push the neutron star in one direction, it can also add or subtract angular momentum. It can spin the neutron star up or slow it down, depending on the geometry of the asymmetry. This is one reason why neutron stars are born with a range of spin rates rather than all having exactly the same rotation period. The details of the explosion matter. The magnetic field of the collapsing core also plays a crucial role. Just as angular momentum is conserved during the collapse, so too is magnetic flux. The magnetic field lines are frozen into the conducting plasma of the stellar core. As the core shrinks, those field lines are compressed into a smaller area. The strength of the magnetic field increases roughly as the square of the decrease in radius, the same scaling law as for angular momentum. This means a modest magnetic field in the pre-collapse core becomes an extraordinarily powerful magnetic field in the neutron star. A massive star's core might have a magnetic field of about 100 Tesla before collapse. After the radius decreases by a factor of 600, the magnetic field increases by a factor of about 360,000, reaching tens of millions of Tesla. Some neutron stars end up with even stronger fields, up to 100 million or even 100 billion Tesla in the case of magnetars. These ultra-strong fields might result from dynamo processes during the first seconds of the neutron star's life, when the hot, convecting, rapidly rotating material generates additional magnetic flux. This amplified magnetic field has a direct consequence for the neutron star's spin. The powerful magnetic field extends far beyond the neutron star's surface, reaching into the surrounding space. As the neutron star rotates, this rotating magnetic field acts like a brake. It accelerates charged particles in the vicinity, flinging them outward and generating electromagnetic radiation. This process extracts a rotational energy from the neutron star, gradually slowing it down. It's called magnetic dipole braking, and it's the primary mechanism by which neutron stars lose rotational energy over time. This braking effect means that neutron stars are fastest right when they're born. From the moment of their creation, they begin to slow down. A neutron star born spinning at several hundred rotations per second will gradually decelerate over thousands, millions, and eventually billions of years. Young neutron stars spin fast. Old neutron stars spin slowly. This is a general rule, and it allows astronomers to estimate the age of a neutron star by measuring how fast it's spinning and how quickly it's slowing down. The Crab pulsar, for example, is about 970 years old, dating back to the supernova observed in 1054. It currently rotates about 30 times per second and is measurably slowing down. By measuring its current spin rate and its rate of deceleration, astronomers can calculate how fast it was spinning when it was born. The answer is roughly 50 rotations per second. In less than 1,000 years, it has already slowed from about 50 spins per second to 30. Over the next several million years, it will continue to slow down until it eventually reaches a spin rate of just a few times per second or less. This gradual slowdown is the natural fate of all neutron stars. They are born spinning fast, and they spend the rest of their existence slowing down. The magnetic field acts as a relentless brake, extracting energy from the rotation and converting it into radiation and particle acceleration. Given enough time, every neutron star should slow down to a lazy spin rate of once every few seconds or even longer. And this is where a profound mystery emerges. Because when astronomers survey the population of known neutron stars, they find something that doesn't fit this picture. They find neutron stars that are spinning far too fast for their age. Neutron stars that should have slowed down long ago, but are instead spinning hundreds of times per second. These are old neutron stars, billions of years old, that have somehow been spun back up to extraordinary rotation rates, neutron stars that are rotating faster than the Crab pulsar, a neutron star that's less than 1,000 years old. How can an ancient neutron star spin faster than a young one? The natural process of magnetic braking should have slowed these old neutron stars to a crawl billions of years ago. Something has intervened. Something has poured angular momentum back into these dead, slowing remnants and resurrected their spin. These are the millisecond pulsars. And their existence points to a second mechanism, completely different from the collapse itself, that can spin a neutron star up to speeds that push the very limits of what matter can withstand. That mechanism is not about compression. It's not about getting smaller. It's about getting fed. And what happens when a neutron star has a companion star willing to donate its mass is one of the most extraordinary processes in all of astrophysics. So we have these extraordinary objects, neutron stars, born from the catastrophic collapse of massive stellar cores, spinning at rates that would be absurd for anything else in the universe, and gradually slowing down over millions and billions of years as their powerful magnetic fields drain away their rotational energy. We understand the physics. Conservation of angular momentum during collapse explains the extreme spin. Magnetic braking explains the gradual slowdown. The theory is elegant and complete. But here's the thing about neutron stars. For a long time, they were entirely theoretical. They existed only on paper, in the equations of physicists who imagined what might happen when matter was compressed to the density of an atomic nucleus. The idea was first proposed in 1934, just 2 years after the neutron itself was discovered. Two astronomers, Walter Baade and Fritz Zwicky, suggested that during a supernova explosion, the core of a massive star might collapse to form a tiny, incredibly dense star composed mostly of neutrons. They predicted the basic properties, small and extraordinarily dense, with immense gravitational fields, but nobody could figure out how to actually find one. A neutron star is only about 20 kilometers across. Even the nearest one would be impossibly small and faint to see directly with an optical telescope. It would be like trying to spot a marble sitting on the surface of the moon. The technology didn't exist. The methods didn't exist. For over 30 years, neutron stars remained a theoretical curiosity. Most astronomers assumed they probably existed, but no one had ever detected one. Some wondered if they ever would. Then, in 1967, a graduate student in Cambridge, England, made one of the most unexpected discoveries in the history of science, and she almost missed it. Jocelyn Bell Burnell was a 24-year-old PhD student working under her advisor, Anthony Hewish. She had helped build a massive radio telescope, a field of poles and wires covering 4.5 acres of the English countryside. The telescope wasn't designed to look for neutron stars. It was designed to study quasars, extremely distant and luminous objects powered by supermassive black holes in the centers of distant galaxies. The telescope worked by detecting radio waves from space, converting them into signals that were recorded on paper chart recorders. Rolls and rolls of paper, covered in squiggly lines, recording the radio signals from the sky. It was Bell Burnell's job to analyze this data. Hundreds of feet of chart paper every day, examining it by eye for anything unusual. In August of 1967, she noticed something strange. A small, repeating signal that didn't look like anything she'd seen before. It wasn't the broad, noisy signature of a quasar. It wasn't interference from human-made electronics, though she initially suspected it might be. It was a series of remarkably regular pulses, evenly spaced, repeating with extraordinary precision. The pulses came every 1.337 seconds, not approximately, every 1.3 seconds. Exactly 1.337 seconds. With a regularity that seemed almost mechanical, Bell Burnell flagged the signal and brought it to Hewish's attention. At first, they couldn't explain it. No known natural source produced such regular pulses. Human-made interference was considered, but the signal moved with the stars, rising and setting at the same time each day, which meant it was coming from space, not from something on Earth. They checked and rechecked. The signal was real. It was coming from a specific point in the sky, and it was pulsing with a precision that rivaled the best clocks on Earth. The regularity was so startling that the research team briefly considered the possibility that they had detected a signal from an extraterrestrial civilization. They gave the source the informal designation LGM1. LGM stood for Little Green Men. This wasn't entirely a joke. The signal was so precise, so unlike anything natural they could imagine, that an artificial origin seemed worth considering. For a brief period, Belle Burnell and her colleagues faced the extraordinary possibility that they might be the first humans to detect evidence of intelligent life elsewhere in the universe. But then Belle Burnell found a second pulsing source, and then a third, and then a fourth. Each one had a different pulse rate, but all shared the same characteristics. Extremely regular pulses, precise timing, coming from different locations in the sky. The discovery of multiple sources made the extraterrestrial hypothesis much less likely. It seemed improbable that multiple alien civilizations in different parts of the galaxy would all be sending the same type of signal. A natural explanation was far more likely. The question was, what natural object could produce such regular pulses? What mechanism in the cosmos could create a signal with clock-like precision, repeating identically, tirelessly, without any variation? The answer came relatively quickly once the right people started thinking about it. Thomas Gold, an astronomer at Cornell University, proposed in 1968 that the pulsing sources were rapidly rotating neutron stars. His reasoning was elegant. A neutron star rotates. It has a powerful magnetic field. The magnetic axis is tilted relative to the rotation axis, just as Earth's magnetic poles are offset from its geographic poles. The magnetic field channels radiation into two beams, one from each magnetic pole, shooting outward into space. As the neutron star rotates, these beams sweep across the sky like the beams from a lighthouse. If you happen to be in the path of one of those beams, you see a flash of radiation every time the beam sweeps past you, one flash per rotation. If the neutron star rotates 30 times per second, you see 30 flashes per second. If it rotates once every 1.337 seconds, you see one flash every 1.337 seconds. The regularity of the pulses directly reflects the regularity of the rotation. And neutron stars, being incredibly massive, incredibly compact, and spinning in the near vacuum of space with almost no friction, rotate with extraordinary precision. There's very little to disturb their rotation. They are, in effect, natural clocks of astonishing accuracy. Gold's proposal was confirmed when a pulsar was discovered at the center of the Crab Nebula. The Crab Nebula is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. If pulsars were rotating neutron stars, and if neutron stars were created in supernovae, then there should be a pulsar at the center of this known supernova remnant. And there was. The Crab pulsar was found pulsing at about 30 times per second, exactly where the theory predicted a neutron star should be. This was powerful confirmation. The connection between supernovae, neutron stars, and pulsars was established. The discovery earned Anthony Hewish the Nobel Prize in Physics in 1974. Controversially, Jocelyn Bell Burnell, who actually found the first pulsar, was not included in the prize. This omission has been widely criticized in the decades since. Many astronomers and physicists consider it one of the greatest injustices in the history of the Nobel Prize. Belle Burnell herself has been remarkably gracious about the oversight, but the scientific community broadly agrees that she deserved recognition. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million, which she donated entirely to fund scholarships for women, underrepresented ethnic minorities, and refugee students pursuing physics research. Now let's talk about the lighthouse model in more detail, because the mechanism that creates pulsar beams is remarkable in its own right. A neutron star's magnetic field is enormously powerful, as we discussed. This field has a dipole structure, meaning it has a north pole and a south pole, just like a bar magnet or like Earth's magnetic field. But unlike Earth's magnetic field, which is relatively weak, the neutron star's field is so intense that it dominates the physics of everything around the star. Charged particles near the neutron star, electrons and positrons, are caught by this magnetic field. They can't move freely. Instead, they're forced to follow the magnetic field lines, spiraling along them like beads on a wire. Near the magnetic poles, these field lines converge. Particles are funneled along the converging field lines toward the poles, and as they accelerate along these curved paths, they emit radiation. This radiation is concentrated into narrow beams that emerge from the magnetic poles. The key detail is that the magnetic axis doesn't have to be aligned with the rotation axis. In fact, it usually isn't. Just as Earth's magnetic north pole is offset from its geographic north pole by about 11 degrees, a neutron star's magnetic poles are typically tilted relative to its spin axis. This tilt is what makes a pulsar a pulsar. As the star rotates, the magnetic poles trace circles around the spin axis, and the beams of radiation sweep through space along those circles. Think of holding a flashlight at an angle while spinning around in a circle. The beam of the flashlight traces a cone shape in space. Anyone standing in the path of that cone sees a flash of light each time the beam sweeps past them. If they're outside the cone, they see nothing. The same is true for pulsars. We only detect a pulsar if its beam happens to sweep across Earth during each rotation. If the beam is pointed in a different direction, we'd never know the neutron star was there, at least not from its pulsed emission. This means that for every pulsar we detect, there are many more neutron stars whose beams miss us entirely. Estimates suggest that we only detect about 10 to 20% of the pulsars in our galaxy. The rest are spinning away in silence, their beams sweeping through empty space where no one is watching. The radiation from pulsars spans a wide range of the electromagnetic spectrum. Most pulsars were originally detected at radio wavelengths because radio telescopes were the first instruments sensitive enough to detect the pulsed signals. But many pulsars also emit at higher energies. The Crab pulsar, for instance, emits pulsed radiation across the entire electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and even gamma rays. It's one of the few pulsars bright enough to be seen with an optical telescope, flashing 30 times per second in visible light. If your eyes could process images fast enough, you'd see the Crab pulsar blinking on and off 30 times every second. What makes pulsars truly remarkable, beyond their extreme physical properties, is their regularity. Pulsar timing is extraordinarily precise. The pulsars arrive with a regularity that rivals, and in some cases exceeds, the best atomic clocks on Earth. Some millisecond pulsars, the fastest spinning ones, have pulse arrival times that are stable to within a few hundred nanoseconds over periods of years. A nanosecond is 1/billionth of a second. These objects are keeping time with a precision of a few hundred billionths of a second per pulse, maintained consistently over years and decades. This precision is a direct consequence of the neutron star's enormous moment of inertia. The neutron star contains more mass than the Sun, packed into a sphere 20 kilometers across. Spinning this object at hundreds of rotations per second means it has an enormous amount of rotational energy. Any disturbance, any force that might speed up or slow down the rotation, has to fight against this massive reservoir of rotational energy. It's like trying to change the speed of an enormous flywheel by tapping it with your finger. The flywheel is so massive and spinning so fast that your tap has virtually no effect. The same is true for neutron stars. Small perturbations barely affect the rotation rate because the rotational energy is so colossal. This precision has turned pulsars into one of the most valuable tools in astrophysics, useful far beyond just studying neutron stars themselves. Pulsar timing has been used to test Einstein's general theory of relativity with extraordinary accuracy. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar in orbit around another neutron star. By precisely timing the pulses from this binary pulsar over many years, they measured the orbital decay of the system. The two neutron stars were slowly spiraling toward each other, losing orbital energy. The rate of this spiral matched exactly what general relativity predicted should happen if the system was emitting gravitational waves, ripples in the fabric of space-time itself. This was the first indirect evidence for gravitational waves, decades before they were directly detected by LIGO in 2015. Hulse and Taylor received the Nobel Prize in 1993 for this discovery. Pulsar timing arrays are now being used to detect gravitational waves directly. By monitoring dozens of millisecond pulsars spread across the sky and looking for correlated variations in their pulse arrival times, astronomers can detect the stretching and squeezing of space-time caused by passing gravitational waves. In 2023, several pulsar timing array collaborations around the world announced evidence for a background hum of gravitational waves permeating the universe, likely produced by merging supermassive black holes in distant galaxies. Pulsars are being used as a galaxy-sized gravitational wave detector, turning the regularity of their rotation into one of the most sensitive measurement tools ever devised. Pulsars have even been proposed as a navigation system for spacecraft. Because each pulsar has a unique pulse profile and a precisely known position, a spacecraft equipped with an X-ray detector could determine its position in the solar system by measuring the arrival times of pulses from several known pulsars. This is essentially a cosmic version of GPS. NASA tested this concept in 2017-18 with an experiment called Sextant aboard the International Space Station, using an X-ray telescope to detect pulses from millisecond pulsars and demonstrating that the technique could determine the station's position to within about 5 kilometers. Future deep space missions might use pulsars for autonomous navigation when they're too far from Earth for conventional tracking. Now, let's talk about the population of known pulsars and what they tell us about neutron star spin. As of today, astronomers have discovered over 3,400 pulsars. Most of these were found through systematic radio surveys that scan the sky looking for periodic signals. The population of known pulsars spans an enormous range of rotation rates, from the slowest pulsars that rotate once every few seconds to the fastest that spin hundreds of times per second. When astronomers plot the known pulsars on a diagram showing their spin period on one axis and their rate of slowdown on the other, a clear pattern emerges. This diagram is called the PP dot diagram, where P is the period and P dot is how fast the period is changing. It's one of the most important tools in pulsar astronomy because it reveals the life stories of these objects at a glance. Most ordinary pulsars, the ones born in supernovae, cluster in one region of this diagram. They have periods ranging from about 1/10 of a second to several seconds, and they're slowing down at rates that are consistent with magnetic braking. Young pulsars are in the upper left of the diagram, spinning relatively fast and slowing down relatively quickly. As they age, they migrate toward the lower right, spinning more slowly and decelerating less rapidly. The path a pulsar follows across this diagram traces out its life history. Eventually, as a pulsar slows down enough, something happens. The mechanism that produces the radio beam becomes less efficient. The pulsar crosses what astronomers call the death line. Below this line, the pulsar's magnetic field and rotation rate are no longer sufficient to generate the particle acceleration needed to produce detectable radiation. The pulsar goes silent. It's still there, still spinning, still a neutron star, but it's no longer producing detectable pulses. It becomes invisible to our radio telescopes. There are almost certainly billions of these dead pulsars scattered throughout the galaxy. Ancient neutron stars that long ago crossed the death line and faded into silence. Dark, cold, spinning slowly, drifting through space as invisible relics of stars that died billions of years ago. But there is a second population on the PP dot diagram that doesn't fit this tidy story at all. Down in the lower left corner, separated from the main population, sits a cluster of pulsars with very short periods, spinning many hundreds of times per second, but with very low slowdown rates. These are the millisecond pulsars, and they are deeply, fundamentally puzzling. If you trace the normal evolutionary path of a pulsar, moving from the upper left to the lower right as it ages and slows, you'd never end up in the lower left corner. The normal path doesn't go there. A neutron star born spinning fast gradually moves rightward and downward on the diagram as it ages. It doesn't jump to the lower left. To reach the lower left corner where millisecond pulsars live, something unusual has to happen. Something has to take an old, slow neutron star and spin it back up, increasing its rotation rate while simultaneously reducing its magnetic field. Something has to reverse the natural aging process of a pulsar, rejuvenating it, making it spin fast again. The millisecond pulsars present a genuine paradox when you first encounter them. They spin faster than most newborn pulsars, yet they're clearly not young. We know they're not young for several reasons. Their magnetic fields are much weaker than those of young pulsars, typically 1,000 to 10,000 times weaker. Strong magnetic fields naturally decay over time, so weak fields indicate great age. Many millisecond pulsars are found in globular clusters, dense collections of old stars where star formation ceased billions of years ago. No supernovae have occurred in these clusters for a very long time, so any neutron stars there must be ancient. And the low slowdown rates of millisecond pulsars mean they're losing rotational energy very gradually, which is consistent with weak magnetic fields and old age. So we have old neutron stars spinning at rates that exceed those of young neutron stars. Stars that should have crossed the death line long ago and faded into invisibility are instead among the most rapidly rotating objects in the known universe. Their rotation rates range from about 1.4 milliseconds to about 30 milliseconds per period. The fastest, PSRJ 1748-2446 AD, completes 716 rotations every second. This is an ancient neutron star, probably several billion years old, spinning faster than any young pulsar we've ever observed. How is this possible? The answer lies in something we haven't discussed yet. Most millisecond pulsars have a companion. They're not alone in space. They exist in binary systems, orbiting together with another star. And this turns out to be the critical clue. When astronomers first surveyed millisecond pulsars, they noticed a striking pattern. About 80% of them are in binary systems, orbiting with a companion star. This is a much higher binary fraction than for normal pulsars. Among ordinary pulsars born in supernovae, only about 1% are in binaries. The supernova explosion that creates the neutron star usually disrupts the binary system. The explosion is asymmetric and violent. It kicks the neutron star in one direction and blows the companion star in another, or destroys the companion entirely. Most neutron stars born in supernovae end up alone, single objects hurtling through space. But millisecond pulsars are different. Most of them have companions, and those companions are often unusual stars. Many are white dwarfs, the dense remnants of lower mass stars that have completed their evolution. Others are low mass stars that appear to have been partially consumed, stripped of much of their outer material. The companions show signs of having lost mass, and that mass had to go somewhere. It went to the neutron star. Over millions of years, matter flowed from the companion star onto the neutron star. This process is called accretion, and it's the key to understanding millisecond pulsars. As matter falls from the companion onto the neutron star, it doesn't fall straight down. It carries angular momentum with it. The infalling matter forms a swirling disk around the neutron star, spiraling inward and gradually transferring its angular momentum to the neutron star. Each bit of matter that lands on the neutron star's surface gives it a tiny push, spinning it up just a little bit faster. Over millions of years, the accumulated effect of all this infalling matter is enormous. The neutron star is gradually spun up from a slow rotation to hundreds of rotations per second. This is the recycling mechanism. Old dead pulsars are recycled, brought back to life by the angular momentum donated by a companion star. The process takes a very long time, typically hundreds of millions of years. During this time, the neutron star is visible not as a radio pulsar, but as an X-ray binary. The infalling matter heats it up as it spirals toward the neutron star, reaching temperatures of millions of degrees and emitting X-rays. X-ray astronomers have observed many such systems. Neutron stars surrounded by glowing accretion disks, actively being spun up by mass transfer from their companions. Eventually, the companion star runs out of material to donate, or the neutron star's increasing spin generates enough radiation pressure to blow the remaining matter away. The accretion stops, the disk disperses, and what's left is a rapidly spinning neutron star with a weak magnetic field, now visible again as a radio pulsar, a millisecond pulsar, recycled from the dead, resurrected by the matter and angular momentum of a companion star. This recycling process also explains why millisecond pulsars have weaker magnetic fields than young pulsars. The accretion process itself is thought to bury or reduce the neutron star's magnetic field. As matter piles onto the surface, it pushes the magnetic field lines inward, effectively screening the field. Additionally, the long timescales involved, hundreds of millions to billions of years, allow natural magnetic field decay to further weaken the field. The combination of accretion-driven burial and time-dependent decay produces the weak fields characteristic of millisecond pulsars. The weak field is actually essential to the millisecond pulsar's survival as a fast spinner. Remember, the magnetic field acts as a brake. A strong field slows the neutron star down rapidly. If a millisecond pulsar had the same strong field as a young pulsar, it would slow down quickly and wouldn't remain a fast spinner for long. But with a weak field, the braking is gentle. The millisecond pulsar loses rotational energy very slowly, maintaining its rapid spin for billions of years. Some millisecond pulsars will continue spinning at close to their current rates, for longer than the current age of the universe. They are, in a sense, perpetual motion machines, not truly perpetual, but so close to it that the difference is negligible on any human timescale. The evidence for this recycling scenario is now overwhelming. Astronomers have observed systems at every stage of the process. They've seen neutron stars actively accreting from companions in X-ray binaries. They've seen transitional systems that switch between an accretion-powered X-ray state and a rotation-powered radio pulsar state on timescales of weeks. They've even caught a system in the act of switching, transforming from an X-ray binary to a millisecond pulsar in real time. The evolutionary sequence from ordinary pulsar to dead pulsar to X-ray binary to millisecond pulsar is well established, supported by observations, theory, and computer simulations. And so, the story of why neutron stars spin so fast has two acts. The first is about birth. A massive star dies, its core collapses. Conservation of angular momentum amplifies a slow rotation into a furious spin. The neutron star is born rotating tens or hundreds of times per second. Over millions of years, magnetic braking slows it down. Eventually, it crosses the death line and goes silent. This is the natural life cycle of an ordinary pulsar. The second act is about resurrection. A dead or dying pulsar in a binary system receives matter from its companion star. The infalling matter carries angular momentum that spins the neutron star back up. Over hundreds of millions of years, the neutron star is recycled into a millisecond pulsar, spinning hundreds of times per second, faster than most newborn pulsars, despite being billions of years old. The weak magnetic field that results from the accretion process ensures that the millisecond pulsar will maintain its rapid spin for an extraordinarily long time. Both chapters involve angular momentum. In the first, angular momentum is conserved during collapse, amplifying a slow spin into a fast one. In the second, Angular momentum is transferred from infalling matter, spinning an old neutron star back up to extreme rotation rates. The same fundamental quantity, angular momentum, drives both processes, one through compression, the other through accretion, two completely different physical mechanisms, both producing the same extraordinary result, neutron stars that spin at rates that challenge our ability to comprehend them. So now we know the full story, or at least we think we do. Neutron stars are born spinning fast because of the conservation of angular momentum during the collapse of a massive star's core. They slow down over time because their powerful magnetic fields act as brakes. And some of them are spun back up to extraordinary rotation rates by accreting matter from a companion star. Two mechanisms, both rooted in angular momentum, producing the fastest spinning objects in the known universe. But deeper questions are hiding inside this story. Questions that take us to the absolute frontier of physics. Questions about what matter itself is made of at the most extreme densities and pressures. Questions about the fundamental limits of rotation. And questions about what neutron stars can teach us about the universe that no laboratory on Earth could ever reveal. Let's start with a question that seems simple, but turns out to be extraordinarily profound. How fast can a neutron star actually spin? Is there a maximum rotation rate? A speed limit beyond which no neutron star can go without destroying itself? The answer is yes. There is a limit. And understanding that limit takes us deep into the physics of matter under extreme conditions. Every spinning object experiences centrifugal effects. The rotation creates an outward force at the equator that opposes gravity's inward pull. For most objects, gravity wins easily. The Earth rotates once every 24 hours, and the centrifugal effect at the equator is tiny compared to gravity. You weigh about 0.5% less at the equator than at the poles because of Earth's rotation, but that's a trivial difference. Gravity dominates overwhelmingly, but as rotation speed increases, the centrifugal effect grows. Specifically, it grows with the square of the rotation rate. Double the spin, and the outward force quadruples. At some critical rotation rate, the centrifugal force at the equator exactly equals the gravitational force holding the object together. Beyond that point, matter at the equator would be flung into space. The object would tear itself apart, shedding material from its equator until it slowed down enough to stabilize. For a neutron star, this critical rotation rate is called the mass shedding limit, or the Keplerian limit. It depends on the neutron star's mass, its radius, and therefore how dense it is. A typical neutron star with about 1.5 solar masses and a radius of about 10 kilometers has a mass shedding limit of roughly 1,000 to 2,000 rotations per second, depending on exactly how the matter inside it behaves under compression. That's an incredibly fast rotation rate. The equatorial surface at that speed would be moving at a significant fraction of the speed of light. The fastest known pulsar, PSRJ 1748-2446 AD, rotates at 716 times per second. That's fast. Astonishingly fast. But it's still well below the theoretical mass shedding limit. This raises an interesting question. Why don't we see neutron stars spinning even faster? If the theoretical limit is somewhere around 1,000 to 2,000 rotations per second, and the fastest we've observed is 716, what's stopping them from spinning up further? There are several possible explanations, and each one tells us something important about the physics involved. One possibility is that we simply haven't found a faster one yet. The fastest spinning pulsars are the hardest to detect, because their pulse periods are so short. Current radio telescopes have limits on how fast a pulse rate they can resolve, especially when the pulsar signal has been smeared out by its passage through the interstellar medium. The gas and plasma between stars slow down lower frequency radio waves more than higher frequency ones, spreading the pulse out in time and making it harder to detect. For the fastest millisecond pulsars, this smearing effect can be severe enough to hide the signal entirely. There might be neutron stars spinning at 800, 900, or even 1,000 rotations per second that we simply can't detect with current instruments. But there's a more fascinating possibility. There might be a physical mechanism that prevents neutron stars from being spun up past a certain rate. A mechanism that kicks in long before the mass shedding limit is reached. And the leading candidate for this mechanism is gravitational wave emission. Here's how it works. As a neutron star is spun up by accretion, it eventually reaches a rotation rate where tiny asymmetries in its shape become significant. No neutron star is perfectly spherical. The immense pressures and temperatures inside the star, the interactions between the superfluid neutrons in the interior and the rigid crust, the stresses induced by the powerful magnetic field, all of these can create small mountains or bumps on the neutron star's surface. I say mountains, but remember the scale. The largest deformation the crust can sustain is less than a fraction of a millimeter. But even a bump that tiny on an object spinning hundreds of times per second creates a time-varying mass distribution that generates gravitational waves. Gravitational waves carry energy away from the neutron star, and that energy comes from the star's rotation. The gravitational wave emission acts as a brake, opposing the spin-up from accretion. As the neutron star spins faster, the gravitational wave emission becomes stronger because it depends on the rotation rate to a very high power. Specifically, the power radiated in gravitational waves scales roughly as the sixth power of the rotation frequency. This means that if you double the spin rate, the gravitational wave power increases by a factor of roughly 64. This is an incredibly steep relationship. A small increase in spin produces a dramatic increase in gravitational wave output. At some point, the energy being pumped in by accretion exactly balances the energy being radiated away as gravitational waves. The neutron star reaches a spin equilibrium. It can't spin up any further because any additional angular momentum added by accretion is immediately carried away by gravitational radiation. The star is stuck, spinning as fast as this balance allows, unable to accelerate further no matter how much matter continues to fall onto its surface. This gravitational wave spin equilibrium might explain why we don't see neutron stars spinning faster than about 700 or so rotations per second. The accretion process tries to spin them up further, but gravitational wave emission prevents it. The two processes balance each other, creating a ceiling on the achievable spin rate. If this hypothesis is correct, it has a remarkable implication. The fastest spinning millisecond pulsars should be emitting continuous gravitational waves right now, not the brief, intense bursts of gravitational waves produced by colliding neutron stars or merging black holes, but a steady, continuous hum of gravitational radiation. Current gravitational wave detectors like LIGO and Virgo are actively searching for these signals. They haven't detected them yet, but the next generation of detectors with improved sensitivity might succeed. Detecting continuous gravitational waves from a spinning neutron star would be a major breakthrough, confirming our understanding of both neutron star physics and general relativity. Now, here's where the story becomes truly extraordinary. The maximum spin rate of a neutron star, whether it's set by the mass shedding limit or by gravitational wave equilibrium, depends critically on what the neutron star is made of inside. And this connects the study of spinning neutron stars to one of the deepest unsolved problems in physics: the nature of matter at extreme densities. We know what the outer layers of a neutron star are made of. The crust is composed of neutron-rich atomic nuclei arranged in a crystal lattice, similar to a solid metal but far denser. Below the crust, matter transitions to a sea of free neutrons with a small admixture of protons and electrons. These neutrons form a superfluid, a state of matter where the fluid has zero viscosity and can flow without any friction. The protons form a superconductor, a state where electrical current flows without resistance. These exotic states of matter are well understood from laboratory physics, even though the conditions in a neutron star are far beyond what any laboratory can achieve. But deeper inside, in the core, things become uncertain. The density at the center of a neutron star exceeds the density of a normal atomic nucleus by a factor of several. At these densities, we genuinely don't know what happens to matter. Our theories make predictions, but those predictions diverge wildly depending on which theory you use. Some theories predict that at extreme densities, neutrons remain the dominant constituent. Matter in the core is essentially a super dense neutron fluid, with properties governed by the strong nuclear force operating at extreme pressures. Other theories predict that at high enough densities, the neutrons themselves break apart. Neutrons are made of quarks, specifically 3 quarks held together by the strong force. Under normal conditions, quarks are permanently confined inside protons and neutrons. You can never isolate a single quark. The strong force between quarks actually gets stronger as you try to pull them apart. Unlike gravity or electromagnetism, which weaken with distance, this property, called confinement, is one of the strangest features of the strong force. But at the extreme densities inside a neutron star's core, the neutrons are pressed so tightly together that the quarks from neighboring neutrons overlap. The boundaries between individual neutrons dissolve. The quarks might become deconfined, freed from their imprisonment inside neutrons, forming a new state of matter called quark matter, or a quark-gluon plasma. This would be the most fundamental state of matter possible. The raw building blocks of protons and neutrons existing freely in a soup of quarks, and the gluons that normally bind them together. This state of matter hasn't existed freely in the universe since a few microseconds after the Big Bang, when the entire cosmos was a quark-gluon plasma before cooling enough for quarks to combine into protons and neutrons. Still, other theories predict exotic particles might appear. Hyperons, which are heavier cousins of neutrons containing strange quarks, might be produced at very high densities. Kaon condensates, collections of exotic particles called kaons settling into a synchronized quantum state, are another possibility. Each of these different compositions gives the neutron star different physical properties, different compressibility, different stiffness, different sizes for a given mass. And here's the connection to spin. A neutron star made of stiff matter, matter that resists compression strongly, will be larger for a given mass. A larger neutron star has a lower mass-shedding spin limit because the equator is farther from the center and the centrifugal effect is stronger. A neutron star made of soft matter, matter that compresses more easily, will be smaller and denser for the same mass. A smaller, more compact star can spin faster before reaching its mass-shedding limit because the equator is closer to the center and gravity is stronger. This means that the maximum observed spin rate of neutron stars tells us something about the stiffness of matter at nuclear densities. If we observe a neutron star spinning at, say, 1,000 rotations per second, that would rule out certain stiff equations of state that predict larger neutron stars. A neutron star that large would not be able to spin at 1,000 rotations per second without shedding mass from its equator. But certain soft equations of state predict smaller, denser neutron stars that could comfortably reach those speeds without flying apart. Those equations of state would remain consistent with the observation. Conversely, if we never observe neutron stars spinning faster than about 700 rotations per second, it could mean either that gravitational wave equilibrium limits the spin before the mass-shedding limit is reached, or that neutron stars are made of stiff matter, and the mass-shedding limit itself is close to 700 rotations per second. Distinguishing between these possibilities requires additional observations, such as measuring neutron star radii through X-ray observations, or detecting continuous gravitational waves. This is why millisecond pulsars matter far beyond just being curiosities. They are laboratories for fundamental physics. They allow us to probe the behavior of matter at densities that cannot be achieved anywhere else. Not in particle accelerators, not in nuclear reactors, nowhere on Earth. The only place in the universe where matter exists at these densities is inside neutron stars. By studying how fast they spin, how they slow down, how large they are, and what their masses are, we learn about the fundamental nature of matter itself. In recent years, observations have begun to narrow down the possibilities. The discovery of neutron stars with masses around 2 solar masses, significantly heavier than the typical 1.5 solar masses, has already ruled out many soft equations of state. Those equations predict that neutron stars above about 1.5 solar masses should collapse into black holes. The fact that 2 solar mass neutron stars exist and remain stable tells us that nuclear matter is relatively stiff at high densities. It pushes back hard against compression. The NICER instrument aboard the International Space Station has directly measured the radii of several neutron stars by carefully analyzing the X-ray light emitted from hotspots on their surfaces. These hotspots are regions near the magnetic poles where accreted matter crashes onto the neutron star, heating the surface to millions of degrees. The X-ray light from these spots is affected by the neutron star's intense gravity, which bends and distorts the photon paths in ways that depend on the star's mass and radius. By modeling these relativistic effects with extraordinary precision, accounting for the curvature of space-time around the neutron star, the Doppler shifts from the rapid rotation and the temperature distribution across the hotspots, astronomers can extract measurements of the neutron star's actual physical size. These measurements, combined with mass measurements from pulsar timing, are providing the first direct constraints on the relationship between neutron star mass and radius. Each measurement constrains the equation of state further, narrowing the range of possible internal compositions. Every new data point eliminates possibilities, bringing us closer to understanding what matter truly does when crushed to densities that no earthly experiment can replicate. And in 2017, the LIGO and Virgo gravitational wave detectors observed the merger of 2 neutron stars. This event, designated GW170817, was a landmark discovery. Not only was it the first gravitational wave detection from merging neutron stars, but it was also accompanied by electromagnetic radiation across the entire spectrum, from gamma rays to radio waves. Over 70 observatories on Earth and in space turned to observe the aftermath. It was the most observed astronomical event in human history. The gravitational wave signal contained information about the tidal deformability of the neutron stars, how much they distorted each other's shapes as they spiraled together in the final moments before merging. In those last few orbits, each neutron star raised enormous tidal bulges on the other, stretching and squeezing the ultra-dense matter. The size of those tidal bulges depends directly on the internal structure of the neutron stars, on how stiff or soft the matter is inside. Stiffer matter produces larger bulges. Softer matter produces smaller ones. The measurement provided powerful new constraints on the equation of state, ruling out both the very stiffest and the very softest possibilities. All of these observations are converging on a consistent picture. Neutron star matter is moderately stiff. Not as soft as pure quark matter would suggest, but not as stiff as the hardest nuclear matter models predict. The truth lies somewhere in between, and each new observation narrows the range. Within the next decade or two, as more neutron star mergers are detected by increasingly sensitive gravitational wave observatories, and as instruments like NICER and its successors deliver ever more precise radius measurements, we may finally determine the equation of state of dense matter, answering a question that has puzzled physicists for nearly a century. We will know at last what neutron stars are truly made of in their deepest, most inaccessible cores. There's yet another way that a neutron star's spin reveals its internal structure. Occasionally, pulsars do something unexpected. They glitch. A pulsar glitch is a sudden, tiny increase in the rotation rate. The neutron star is gradually slowing down as expected, and then, without warning, it speeds up slightly. The change is small, typically less than 1 part in a million, but it's abrupt and unmistakable. The Vela pulsar, about 11,000 years old and 900 light-years from Earth, is one of the most prolific glitches, experiencing a large glitch roughly every 3 years. Glitches are thought to be caused by interactions between the neutron star's rigid crust and the superfluid neutrons in its interior. As the crust slows down due to magnetic braking, the superfluid interior, which has zero viscosity, continues rotating at its original speed. A speed difference builds up. When it becomes large enough, angular momentum is suddenly transferred from the faster spinning superfluid to the slower crust, causing the crust to jump to a higher spin rate. The existence of glitches confirms that matter at nuclear densities really does form a superfluid. And the size and frequency of glitches provide yet another constraint on the neutron star's internal structure. Yet another clue about what lies beneath that impossibly smooth surface. This brings us full circle. We started with a simple question: why do neutron stars spin so fast? And the answer turned out to involve some of the most fundamental physics in the universe: conservation of angular momentum, the life cycles of massive stars, core collapse supernovae, magnetic braking, accretion in binary systems, gravitational wave emission, the equation of state of ultra-dense matter, the nature of quarks and the strong nuclear force. All of these threads are woven together in the spinning of a neutron star. There's something beautiful about this. A single observable quantity, the rotation rate of a neutron star, connects to so many different areas of physics. You can measure how fast a pulsar is spinning with a radio telescope. That single measurement, a number of rotations per second, encodes information about the star's birth, its history, the supernova that created it, the companion star that may have spun it up, the composition of its interior, and the fundamental laws of nature that govern matter and gravity at the most extreme scales. This is what physics does at its best. It takes something observable, something measurable, and shows how it connects to deep truths about the universe. The spinning of a neutron star isn't just a number. It's a window into the heart of matter itself. A rotating beacon that sends us information about the most extreme conditions in the cosmos, encoded in the timing of its pulses. Consider what we've accomplished as a species. We've detected objects 20 kilometers across, located thousands of light years away. We've measured their rotation rates to a precision of nanoseconds. We've used those measurements to test Einstein's general relativity, to detect gravitational waves, and to constrain the composition of matter at densities beyond anything achievable on Earth. We've done all this from the surface of a small rocky planet, orbiting an ordinary star in the suburbs of an ordinary galaxy. Using telescopes built from metal, glass, and silicon. Using mathematics developed by human minds over centuries. Using physics discovered through careful observation and creative reasoning. Neutron stars don't care about us. They spin in the darkness of space, sending their beams sweeping through the cosmos, indifferent to whether anyone is watching. They've been spinning since before the Earth existed. Some of them will continue spinning long after the sun has died and the Earth has been consumed by its expanding red giant phase. They are relics of dead stars, the compressed corpses of objects that once blazed with the light of 100,000 suns, now reduced to tiny, dark, furiously spinning spheres of nuclear matter. And yet we've found them. We've understood them. We've used them to probe the deepest questions in physics. That's remarkable. That's worth pausing to appreciate. The universe is filled with neutron stars. Astronomers estimate there are roughly 1 billion neutron stars in the Milky Way alone. Most of them are old and dim, their magnetic fields decayed, their beams too faint to detect. They drift through the galaxy as invisible remnants, carrying within them the compressed history of the massive stars from which they were born. The very atoms that make up your body were forged in the hearts of massive stars. Stars that may well have left behind neutron stars when they died. Those spinning remnants and the matter in your hands were born in the same nuclear fires. You are connected to them through the reactions that created both them and you. Some of those billion neutron stars are pulsars, beaming their radiation across space with clockwork precision. Some are millisecond pulsars, ancient objects resurrected by the matter of companion stars, spinning at rates that challenge our understanding of material strength and gravitational physics. Some are magnetars, with magnetic fields so intense they could erase a credit card from farther away than the diameter of Earth and rearrange the atomic structure of matter from 1,000 kilometers away. In 2004, a magnetar on the far side of the galaxy released a burst of energy so powerful that it measurably ionized Earth's upper atmosphere, even from 50,000 light-years away. A dead star, smaller than a city, briefly altered the chemistry of our planet's sky from across the galaxy. Some are in binary systems, slowly spiraling toward mergers that will one day produce gravitational waves detectable from billions of light-years away. And some are simply drifting alone through the void, dark and silent and spinning, carrying their angular momentum from the moment of their creation, slowly winding down over timescales longer than the current age of the universe. Let me leave you with one final thought about what neutron star spin really means. When a massive star dies and its core collapses, the angular momentum that was distributed throughout a volume the size of the Earth is suddenly compressed into a volume the size of a city. That angular momentum doesn't disappear. It can't disappear. The universe doesn't allow it. Instead, it manifests as furious, almost incomprehensible rotation. The slow, stately turning of a stellar core becomes the frantic spinning of a neutron star. It's the same angular momentum, the same rotational motion, the same physical quantity preserved across one of the most violent events in the cosmos. In some ways, the spin of a neutron star is a message from the past. It carries information about the star that existed before. The rotation rate tells us how fast the progenitor star's core was spinning. The direction of the spin axis tells us about the orientation of the original star. The gradual slowdown tells us about the neutron star's magnetic field and its age. And for millisecond pulsars, the rapid spin tells us about a second life, a resurrection through accretion, a dead star given new energy by a companion. Angular momentum is one of those quantities that the universe guards jealously. It can be transferred from one object to another. It can be redistributed within a system, but it can never be created or destroyed. When you watch a figure skater pull in their arms and spin faster, you're watching the same law that governs the birth of neutron stars. The same fundamental quantity that determines whether a neutron star spins 10 times per second or 700. The universe is built on conservation laws. Energy is conserved. Momentum is conserved. Angular momentum is conserved. These laws are absolute, inviolable rules woven into the fabric of reality itself. And when these laws operate at extreme scales, the results are extraordinary. A city-sized object spinning 700 times per second. A surface moving at a quarter of the speed of light. A density where atoms themselves are crushed out of existence. All of these extreme properties flow naturally, inevitably, from simple conservation laws applied to extreme conditions. That's the lesson of neutron stars. The universe doesn't need exotic or mysterious forces to produce extraordinary phenomena. It just needs simple laws operating at extreme scales. Conservation of angular momentum is taught in introductory physics courses. It's demonstrated with bicycle wheels and spinning chairs, and this same simple law, applied to the collapsing core of a massive star, produces the fastest spinning objects in the known universe. The next time you look up at the night sky, consider this. Scattered throughout the darkness, hidden among the stars you can see, are objects so small that you could drive across them in minutes, yet so massive they contain more matter than the sun, spinning so fast that their surfaces move at significant fractions of the speed of light. You can't see them with your eyes, but they're there, billions of them, scattered throughout our galaxy, spinning in the darkness, carrying angular momentum from the deaths of stars that may have died before the Earth was born. Each one a testament to the simple, beautiful, unbreakable laws that govern everything in the universe, from a child on a merry-go-round to the collapsed core of a star. That is why neutron stars spin so fast. Not because of some exotic unknown force, not because of some mysterious cosmic engine, but because of a principle so simple and so fundamental that you can feel it in your own body when you spin around with your arms pulled in tight. The universe takes that principle, applies it to the death of a giant star, and produces something that spins faster than a kitchen blender, weighs more than the sun, and fits inside a single city. Simple laws, extreme scales, extraordinary results. That's the universe we live in. And understanding it, even a little, is one of the greatest privileges of being alive. Thank you for joining me on this journey into the hearts of dead stars. If you found this exploration valuable, a like or a subscribe would mean a lot. It helps me keep making these deep dives into the physics of the cosmos. And remember, the next time someone asks you why neutron stars spin so fast, you can tell them. It's the same reason a figure skater spins faster when they pull in their arms, just scaled up to the most extreme conditions the universe has to offer. Sleep well tonight, knowing that somewhere out there, in the darkness between the stars, a city-sized sphere of neutrons is completing 700 rotations before your next heartbeat. The universe is extraordinary, and so is the fact that you can understand it. Good night.